All right, today we're diving into something pretty radical, a thought experiment that really challenges one of the biggest pillars of modern physics. What if that weird, unchanging speed of light isn't really a fundamental property of the universe? What if it's just an illusion, created by the very act of us looking at it?
So let's kick things off with a pretty bold question. What if the Michelson-Morley experiment, the one that basically set the stage for Einstein's relativity, wasn't actually uncovering some deep cosmic truth? What if it was really pointing to a fundamental mistake in how we even measure the world?
To really get this, we've got to rewind a bit, back to the puzzle that started this whole thing, the bizarrely, stubbornly constant speed of light.
See, in our everyday world, everything makes sense. Speeds add up. If you're on a train that's moving and you throw a ball forward, someone standing on the ground sees that ball moving at the speed of the train plus the speed you threw it. Easy. But light? Man, light was a whole different story. It just refused to play by those rules. It didn't matter how fast you were going, a beam of light from your flashlight always moves away from you at the exact same speed. This was a huge crisis for physics back in the 19th century. It seemed completely impossible.
So, along comes Einstein with this absolutely revolutionary idea. He said, hey, maybe the problem isn't with light. Maybe it's with space and time in themselves. He proposed that they're woven together into this single fabric called space-time. And that fabric can literally stretch and shrink to make sure that everybody, no matter how they're moving, measures the exact same speed of light. And that's been the bedrock of physics for more than 100 years.
But what if there's another way to look at this? What if space-time doesn't have to warp at all? What if this whole paradox is just a kind of artifact, a side effect of the geometry of how we observe things in the first place? To wrap our heads around this, let's build a new metaphor. We're going to break down the process of seeing reality into three totally distinct parts.
First up, we've got something called the public space. Now, don't think of this as space you can, walk through. Think of it as the ultimate source of all reality. A huge conceptual shell that contains all possible information, almost like a shimmering cloud of sparks. Second, picture this, the information sphere. Think of it like a giant cosmic camera sensor. It's the surface where all those raw sparks from the public space get captured, and for the very first time, they get some kind of structure. This is raw potential turning into organized information.
And third, we have the mathematical plane. This is our world, right? The world as we experience it. It's the flat grid where we do our science, make our measurements, and build our theories. But here's the crucial bit you have to remember. This plane is our map of reality. It is not reality itself.
So how do all these pieces fit together? Well, the information doesn't just hang out on the sphere. It gets projected onto our mathematical plane. And this is the core idea, beautifully simple. What we perceive and what we measure as reality is just a projection, a shadow, of a much deeper, more complex, higher dimensional structure of information. So let's break that down. It's not a single thing that happens. It's really a two-step translation of information, kind of like a stamp being pressed down twice.
Okay, so here's how it works. Step 1. Those raw sparks from the public space get stamped onto the surface of the information sphere. That's where the data gets organized. Step 2. We observe the projection, the shadow of that sphere on our mathematical plane, and that shadow, that's the world we experience.
All right, let's take this whole new way of thinking and apply it to that classic Michelson-Morley experiment. We're going to reimagine it, not sitting on a lab bench, but taking place inside a vast conceptual room. So, the old way of thinking, you've got this flat device, and light shoots out from the middle. But in our new model, the apparatus is a flat disk inside a giant, spherical room. And here is the absolute key difference. The light doesn't start at the center. It starts everywhere, on the walls, that public space, and it travels inwards, converging on the center. Okay, now this is where things get really interesting. What happens when we add motion to the mix? This is where the model shows its true power, because it's not warping space, it's warping the message itself. So let's ask the million-dollar question. What happens to all that light converging on the center when the entire system, the spherical room and the little detector disk inside, is blasting through space at, say, 60% of the speed of light? If the room is just sitting there, no problem. Light from every single spot on the wall arrives at the center at the exact same time. But when you're moving, everything changes. The detector is rushing towards the light coming from the front wall, so it catches that light early. At the same time, it's running away from the light coming from the back wall, so that light has to play catch-up, and it arrives late. And the difference?
It's not small, it's huge. At 60% of light speed, the information from the front gets there 4 times faster than the information from the back. That's a massive distortion. And here's the kicker, the real payoff. Space-time didn't have to warp at all. The message itself got warped by our motion. We're sampling the information from different directions at different times. It's just like a Doppler effect, but not for sound, for reality itself.
So what does this all mean? What's the big takeaway here? This thought experiment, it really forces us to completely reconsider the rules we thought governed our reality.
The big paradigm-shifting idea is this. The constant speed of light isn't some deep, fundamental law of the universe. It's a side effect. It's an artifact of observation. It's simply what you get when you forget that moving through space fundamentally changes how you sample information from the world around you.
And this really gets at what this model sees as the fundamental mistake of classical physics. It assumed this sort of God's eye view. It pretended we could look at a whole plane of reality and know what's happening everywhere on it all at once. It completely forgot that observation is a real physical process. It takes time. The light actually has to travel from the walls to our detector, and that journey, that procedure, that's the missing piece of the whole puzzle.
Which leaves us with one last, truly mind-bending question to chew on. Is reality some fixed stage that we're all just actors on? Or is what we call reality something that is actively being created, moment by moment, by the very act of us observing it? That's a question that could change everything.